In today's lecture, we're going to talk mostly about matter and energy. So here you can see a dietitian doctor who teaches that young boy how to eat right. And we're going to talk about all things matter first. So what is matter? Matter is anything that makes up things. For instance, copper makes up pennies, and this is an example of a matter. Matter is anything that has mass and occupies space. According to its composition, matter can be classified into pure substances, which composition is fixed and definite. For example, water or glucose. Matter also can be classified as a mixture. Mixtures contain two or more different substances. Substances that are physically mixed but not combined chemically. For instance, if you will mix salt and baking soda, it's going to be a mixture that consists of two different substances. If you will dissolve salt in water, that also will be a mixture which contains independently water and sodium chloride. So let's talk about pure substances first. Pure substance is a type of matter with a definite composition. If we are talking about an element, then elements, all elements, pure substances that are elements, are composed of one type of atom. For instance, aluminum or iron. A compound is composed of two or more elements, two or more types of atoms. But in a compound, in a specific compound, those elements are always combined in the same proportion. For instance, in a molecule of water, you already see that you're going to have two atoms of hydrogen and one atom of oxygen. So here are a few examples of elements here. We already gave you iron and aluminum, lead or copper. Those are elements. Here's the compound. In addition to what I was talking about water, you can see sugar, or sucrose, sodium chloride, and hydrogen peroxide. They all contain two or more elements in a definite ratio. So, for instance, interestingly, if you will take a compound like table salt, sodium chloride, each individual element that comprises it, sodium, metal, and chlorine gas, they look completely different compared to the combination of them that produces sodium chloride. Now let's talk a little bit more about mixtures. So mixture consists of two or more substances. Importantly, those substances are not chemically combined, and the substances that make up a mixture can be separated by physical methods without application of any chemical modifications. So mixture can be homogeneous or heterogeneous. Homogeneous mixture has the uniform composition throughout, and different parts of the mixture cannot be visualized with the naked eye. Brass is a homogeneous mixture of copper and zinc, for instance. Breathing mixtures for scuba diving are another great example of homogeneous mixtures. So nitrox, heliox, trimix all have mixtures of different gases. So for instance, for nitrox, it's the mixture of oxygen and nitrogen. Heliox, oxygen and helium. For trimix, oxygen, helium, and nitrogen gases. Now, heterogeneous mixture contains clearly visible parts, and the composition varies from one part of the mixture to another. So say you combine water and pennies, water and copper, to chemicals, to substances, and that's the heterogeneous mixture. If you will add sand to water, that will be a heterogeneous mixture. So this is the classification of matter here. Let's review it one more time. So matter can be divided into pure substances versus mixtures. Pure substances can be elements that consist of one type of atoms, and compounds that have definite, if not changing composition, of more than two atoms. Mixtures can be homogeneous, where individual parts cannot be visualized, and they have the same composition throughout. And heterogeneous, in which individual parts of the mixture can be visualized, and the composition may change from one part of the mixture to another. Now, matter can exist in different states. As you all know, water can be liquid, it can be gaseous or solid. So, solid state of matter has a definite shape, a definite volume. Particles in the solid move, but move extremely slowly, and we're talking atoms, of course, atoms in the solid are very close together, and they have usually fixed arrangement, often, not always, but often they have fixed arrangement, which we sometimes call crystallic lattice. Liquids, on the other hand, have an indefinite shape. As you know, liquid can occupy the shape of the vial or vessel that it's placed in, its container. However, liquids have definite volume. 1 gallon of milk is 1 gallon of milk. It's not going to suddenly occupy 2 gallons of milk. Particles in the liquid are close together, but they can move. They move relatively slowly, and they do not have sort of fixed arrangement within the liquid. Gases, that's the third form of matter that we're focusing on. Gases have an indefinite shape, obviously, unless you give them the container to occupy, and indefinite volume. So you'll know that you can, so that if you will heat up, for instance, the balloon, it will expand in volume, and if you will cool it down, it will decrease in volume. Particles in gases are far apart from each other, and they move very, very fast. There is a fourth state of matter, which is plasma, but we are not talking about it. So here's in this table, you can see a pretty clear comparison between solids, liquids, and gases, and you should be able to compare the states and identify the state of matter based on its definition. Now, before we move on to chemical properties of matter, we're going to start with the conversation about physical properties. So physical properties of matter are characteristics of matter that can be observed or measured without changing the chemical identity, chemical composition of a substance. Examples of physical properties include shape, physical state, solid, liquid or gas, boiling points, freezing points, magnetic points, density, color. All of those are physical properties. For instance, copper, color-wise, is reddish-orange and shiny. From the thermodynamic and electrodynamic standpoint, it conducts heat and electricity very well, unlike some other substances. It is solid at 25 degrees Celsius and has specific melting and boiling points, which you, of course, do not have to memorize. So in regards to physical properties, there can be a physical change. So physical change happens when substance changes its physical state, changes its physical shape, but does not change the identity of itself and composition of itself. So for instance, when water transitions from solid, from ice, to liquid, to gas, to vapors, it changes its physical state and consequentially may change its physical shape, but it still remains water. So here are some examples of physical changes. We already mentioned water. Copper, that is, the chunk of copper is drawn into wires. Paper is cut. Pepper is ground. Sugar that dissolves in the water. All of those are physical changes. None of those substances actually changes in a chemical fashion. So chemical properties, they describe how a substance can interact with other substances or change into new substances, for instance, decompose. So during chemical change, the original substance is converted into one or more other substances with often new chemical, not often, always new chemical and new physical properties. So new substance that is formed as the result of a chemical change has a new composition, new chemical, and new physical properties. So for instance, when sugar gets caramelized at the high temperature, chemically changes. So for instance, when metal reacts with the air and that produces grainy coating, that's an example of chemical change. Iron rusts, and that's the chemical change. We already mentioned sugar. When wood burns, producing carbon dioxide, water and ashes and coals, that's another example of chemical change. Now let's talk about temperature, the parameter that your physician can take using a thermometer like this. So temperature is a property of an object that tells us how cold or hot an object compared to another object. And it indicates the direction of heat flow, and the direction is that the heat always flows from the object with a higher temperature to the object with a lower temperature. There are various thermometers that allow us to measure a temperature. There are three main temperature scales: Fahrenheit, Celsius, and Kelvin, and their reference points are boiling and freezing of water. So on the Celsius scale, here in the center, water freezes at 0 degrees Celsius and boils at 100. In this scale, the normal body temperature is about 37 degrees. In Kelvin scale, the freezing point of water is 273 Kelvin and boiling is 373 Kelvin, which explains that Kelvin and Celsius, each degree on both scales, degrees are the same, but the reference points are slightly different, well, slightly, by 273 degrees. And Fahrenheit has a completely different scale, where water freezes at 32 and boils at 212. So the difference between the two is 180. So 180 degrees Fahrenheit are equivalent to 100 degrees Celsius. Normal body temperature in this case will be 98.6 degrees Fahrenheit. So essentially the 1 degree Celsius, if you compare these two scales, 1 degree Celsius is equivalent to 1.8 degree Fahrenheit. You can see it here. So we can convert from Celsius to Fahrenheit, and it's relatively simple. So this is the conversion from temperature in Celsius to temperature in Fahrenheit. Okay. This is how we go from, say, 10 degrees Celsius to whatever degrees Fahrenheit. Okay, this is the conversion from degrees Fahrenheit to degrees Celsius. Now, what about Kelvin? So Kelvin is the scale. So it turns out that the coldest temperature possible, and it is true, there is an absolute zero, which is in degrees Celsius, will be negative 273 degrees. On the Kelvin scale, absolute zero is 0 Kelvin. There are no degree symbol in front of Kelvin, just Kelvin, no degrees, just Kelvin. There are no negative temperatures, they're always positive. The unit size is the same as Celsius, I already mentioned that. So if you want to go from Celsius to Kelvin, you just need temperature in degrees Celsius, add 273, and you're going to get temperature in Kelvin. So let's take a look how we calculate temperature. So for instance, you have a person with hypothermia. Body temperature 34.8 degrees Celsius. How do we move from Celsius to Fahrenheit? Well, we're given temperature in Celsius, we need temperature in Fahrenheit. So we need to write down that equation that will allow us to convert Celsius into Fahrenheit. By placing 34.8 into the equation, and knowing that 1.8, the conversion factor, is exact, and 32 is exact, we do the calculation and obtain 94.6 Fahrenheit with 3 significant figures. Next on our agenda is the conversation about energy. Energy is something that basically makes things move, from atoms to water to clouds. Energy is the ability to do work, and it can exist in two main types. It can exist in a form of kinetic and potential energy. The kinetic energy is the energy of movement, swimming, water flowing over the dam, working out, the rock falling from the roof. Potential energy is the energy stored for the use, the later time. So rock at the top of the roof before it falls, water at the top of the dam before it goes down, spring that's compressed, and of course something that interests us, chemical bonds. Chemical bonds in gas, coal, or food. Those chemical bonds, when they are broken down, can release energy. So what is the difference between heat and energy? Heat is more narrow term. It is the energy associated with the movement of particles. And it is measured in joules or calories. Higher heat or thermal energy of the substance is associated with a faster movement of the particles of that substance. Now, energy is measured basically in the same units as heat is, and SI unit for energy and work is a joule. 1,000 joules will be a kilojoule. Now, maybe more familiar to use the energy unit named calorie. 1 calorie is defined as 4.184 joules, and it's an exact measure. And this is the conversion factor associated with calories and joules. A calorie by itself is defined as the amount of energy that is needed to increase the temperature of 1 gram of water by 1 degree Celsius. Just like with joules, 1,000 calories will be a kilocalorie. So this chart compares energy from various resources. You can see, energy from a serving of pasta, energy from 1 gallon of gasoline, energy that's radiated by the sun in 1 second. It's kind of interesting. You should explore it. Now, energy is tightly connected to nutrition. And how do we know what is the nutrient value, what is the energy value of food? We can determine this by using a device known as calorimeter. Calorimeter is used to measure the transfer of heat between the bodies, and it consists of a container, usually made of steel, that's filled with oxygen and very specific amount of water. The calorimeter allows us to measure the heat gained by water, that is, at the same time, the heat lost by whatever sample you put in the calorimeter through the combustion. So, for instance, you put there a sample of food, I don't know, a burger, and you burn it in oxygen. That releases energy stored in a burger, and temperature of water increases. And then we can calculate the energy value of food. So here you have a food sample that burns, okay? That burning releases energy, and that heats up water. We can observe the change in the temperature and then calculate the energy content of food. So in nutrition labels, the nutritional energy value of food is presented in calories. It's so-called large or nutritional calorie, written with a capital C. In other countries, the energy is shown in kilojoules. So 1 large calorie is 1,000 regular calories. So these are three main energy-bearing nutrients found in the food: carbohydrates like sugar, fat, and protein. You should know the energy values. So 4 kilocalories per gram or 17 kilojoules per gram of carbohydrate, same as for protein. Fat is most energy-dense food, which contains 9 kilocalories per gram or 38 kilojoules per gram. Here you see some energy values for some foods. It's interesting to look at. You see that there are some foods that contain no carbohydrates, for instance, like beef or chicken or egg, salmon, and steak. Others that contain a lot of carbohydrates and practically no fat, here, and here. Now, how we calculate the energy that we receive from food? So we need to state the quantities that are given, that are needed, and then use the energy value for each food type, and then calculate the kilojoules or kilocalories rounded to the 10th place. So why is that important? Well, it's important because the amount of energy that is needed in a diet of an adult depends on multiple factors, such as gender, age, level of physical activity, some health issues. So basically, people gain weight when they consume more energy than they spend, and they lose weight when they consume less energy than they spend. Well, now let's talk about an interesting parameter called a specific heat. So, for instance, water has very high specific heat, and this is what keeps temperatures in the coastal areas more moderate, both in the summer and in the winter. Specific heat is the amount of heat that raises the temperature of substance, of 1 gram of substance, by exactly 1 degree Celsius. Specific heat is different for different substances, and the units to measure specific heat are joule per gram degree Celsius in SI system, or calorie per gram degree Celsius in the metric system. So this is essentially what specific heat is. It's a heat that is required to change the temperature of exactly 1 gram of substance by 1 degree Celsius. So for water, specific heat is 1 calorie per gram degree Celsius, or 4.184 joules per gram degree Celsius. Here you can see specific heats for various substances. And specific heat is useful because if we know the specific heat of a substance, we can calculate how much heat was lost or gained by that substance by measuring the mass of the substance and the temperature change. So heat equation will be this: mass multiplied by temperature change by the specific heat. So here you can see sort of a demonstration, grams cancel versus grams in degrees Celsius, and same goes here. Grams get cancelled compared to degrees Celsius. So let's calculate some of the specific heats in the following problems. Let's say 5 grams of water change the temperature by 10 degrees Celsius. So what's the heat in question? So 5 grams multiplied by 10 degrees Celsius multiplied by 1 calorie per gram per degree Celsius gives us 50 calories. So you should be able to calculate the specific heat. Now, changes of state. Matter changes its state when it goes from one to another, from when it absorbs heat, for instance, and it goes from liquid to vapors, or when it goes from solid to liquid by absorbing heat as well. So melting is when substance changes the form from solid to liquid at the melting point. Freezing is when substance changes its state from liquid to solid at the freezing point. Freezing and melting points for substances are the same. For water, it's 0 degrees Celsius, and this process is melting and freezing of physical changes that are reversible. Now, the heat of fusion is the amount of heat that is released when 1 gram of liquid freezes at the freezing point, or the amount of heat that is needed to melt 1 gram of solid at its boiling point. These heats are the same. So, for example, to melt water, you need 80 calories per gram of solid water, gram of ice. And when water freezes, 80 calories per gram of liquid water that goes into the solid state are released. So the conversion factor will be 80 calories per 1 gram of water, or 334 joules per 1 gram of water. So how you calculate? Let's say, remembering that 80 calorie thing, you need to know how much heat you have to use to melt 100 grams of ice. So 80 calories per 1 gram is the conversion factor, multiplied by 100 gram. You will need 8,000 calories. Evaporation and condensation. Evaporation is when molecules on the surface of, let's say, water gain sufficient energy to become gas, and the water condenses when gas molecules lose that energy and form a liquid. So basically, during evaporation, liquid is converted into gas. So at the boiling point, all the water molecules acquire enough energy to form a gas. And during boiling, molecules of liquid move to a gas state throughout the liquid, as well as its surface. When the water boils, what you essentially see are bubbles of water vapor that rise through the water. Sublimation and deposition. Sublimation is the transition from solid directly to gas. For instance, dry ice does it, iodine can do it. And deposition occurs when gas particles change directly to a solid. It's important to understand that during that phase-to-phase transition, it doesn't matter whether it's liquid to solid, liquid to gas, solid to gas. There's no change at the temperature. It all happens at the fixed temperature. Boiling happens at the boiling temperature. Melting happens at the melting temperature. Sublimation happens at the sublimation temperature. Sublimation, for instance, is used to prepare freeze-dried foods for long-term storage. Now, the heat of vaporization is similar in essence to the heat of fusion. Heat of vaporization is the amount of heat that is either absorbed to change 1 gram of liquid to gas at the boiling point, or released when 1 gram of gas condenses into liquid at the boiling point. So for water, for instance, heat of vaporization at the boiling point of 100 degrees Celsius will be 540 calories per gram. Same amount of heat is released when 1 gram of steam changes into the liquid water. So the conversion factor will be 540 calories per 1 gram of water, or 20 to 60 joules per gram of water. So if you want to calculate, say, how much heat do you need to completely convert 20 grams of water in a gas, you need to multiply it by 540 calories per gram, and it'll give you 10,800 calories. Heating curve shows the changes in the temperature of a substance. Okay, and you can see that the solid, this is the heating curve for water. You see that if you take really cold ice, -40 degrees Celsius, and start heating it up, the temperature of ice starts going up, and then at melting point, until the entire chunk of ice turns into water, temperature does not change. Then water gets heat up until it reaches its boiling point, and the temperature of that water/gas mix does not change until the entire body of water is turned into a vapor gas phase. Cooling curve is basically the same, just goes in the opposite direction. So you have steam that cools down, forming water and steam mixture during condensation. Then when all steam is converted into water, water is cooling down, and then forms that slush, water and ice during freezing, and then forms ice. So diagonal lines on the heating curve indicate changes in the temperature for the particular physical state, while horizontal lines demonstrate the changes of state actually. So same goes for cooling curve. Okay, so slopes indicate decrease in temperature, while flat lines demonstrate changes of state. So here are some calculations. So for instance, we need to calculate how much heat in joules needed to convert 15 grams of liquid ethanol, 25 degrees Celsius, to gas at its boiling point, 78 degrees Celsius. We know the specific heat, and we know the heat of vaporization. So this is what we've got. We need kilojoules in the end. So how do we approach this? We draw an approximate heating curve. So we need to calculate how much heat you need to bring ethanol from 25 to 78 degrees Celsius, and then how much heat you need to change it from liquid form to gas at 78. So first you will need a specific heat of ethanol to calculate how much heat you need to warm up ethanol from 25 to 78. So you know the temperature change. It's 78 minus 25. And you know the mass of ethanol. So multiply the mass of ethanol by the temperature change, by the ethanol specific heat, and you receive that's the amount of heat that will bring ethanol, 15 gram of ethanol, from 25 degrees Celsius to 78. Next, you need to calculate how much heat you need to vaporize ethanol. So multiply the mass of ethanol by the heat of vaporization per gram, and you need that amount of energy to vaporize ethanol. So at the end of the day, you adding up the amount of heat that you need to heat ethanol and amount of heat that you need to change it from liquid form to gas form. And that's your answer.